Hello and welcome to the video on hash tables. Today we are going to cover the content on linear search, binary search and hashing functions themselves. First of all, let us understand what is meant by a linear search. Given a set of numbers, we would like to locate a number in a sequential way. For example, if we want to locate 20, we start off from the 0th index into the array, make a comparison. If there is no match, we proceed to the next location and we repeat this process continuously until the desired number is found. So this comprises of element by element comparison, and hence the time complexity of a simple linear search is of the order of n. It is very easy to understand that if the element we want to search appears in the beginning of the list or array, the search takes lesser time, and if it appears at the end of the array, highest time is consumed. So in spite of being a very simple search method to implement, it suffers from the performance issues. Let us consider the binary search method. In this case, given a sequence of numbers stored in the form of an array or list, what we do is we try to search for number 23. So we identify index 0 as the leftmost number, leftmost value, index 9 in this case as the highest number or the rightmost number, and we compute the average value or middle value of L and H to give rise to 4 in this case. So index 4 consists of content 16. Now we try to compare the incoming content 23 with 16. Since 23 is greater than 16, we try to restrict our search area towards the right hand side of this particular sequence. Please note that this is possible if and only if the array is sorted or the numbers are sorted in ascending order. If these numbers are arranged at random, then binary search will not work. So now we focus our attention on this particular area. So in the next iteration, number 23 will be the leftmost number. Highest number remains the same. We compute the mid value of L and H. In this case, it is 7. So the content stored at index 7 is 56. We once again compare 23 with 56. There is no match, but we find that 23 is less than 56. So now our search area is restricted to the left part of this midway. That means we search these three numbers. So out of these three numbers, in the next iteration, we try to find the value of middle. Now this is going to give us m equal to 5. So we try to compare the incoming data of 23 with the data stored at m equal to 5, which is 23. Now if we actually compare these values, there is a match. Now we say that the data is found, and hence we stop. So you can see here that binary search is much better in terms of performance, because at each and every iteration the search area is halved, it is divided by 2. Therefore the complexity of this algorithm, the time complexity, is of the order of log of n. Now it is very easy to trace the sequence of steps if the given set of numbers is 11, 22, 33 and so on and so forth. If we are supposed to find the value 90, then once again we start from L equal to 0, and this will be the value of H, and we try to compare the midpoint, try to compare 90 with M. If the new incoming value is more than the middle value, then we restrict our area of search to the right hand side of mid value. Otherwise we start looking for the occurrence of data in the left part. Now this function will be recursive in nature, and hence we will be able to reach the value 19. So binary search, in spite of involving little elaborate number of computations, it fares much better in terms of time complexity when compared to linear search. Let us consider hashing method. First of all, let us look at the motivation for hashing. Now, if one looks at linear search or binary search, it is very easy to understand that the search time is dependent on the position of element. But if one needs to have a constant search time, then the answer is we go for hashing technique. So basically, a hash table, or as it is also called a hash map, is a data structure that associates inputs or keys with values. Basically, it's an exercise where we try to store the data in such a way that at a later point in time, if the data has to be searched, then the search operation is going to take constant time, irrespective of the value of data we want to search for. Some terms are in order. The first term is called hash. A hash is a value computed from a base input number using a hashing function. For example, a small phone book can act as a hash table. In this case, different set of phone numbers corresponding to different owners will be stored. A simple example is shown here. Given a list of items, now these actually act as keys, I design a hash function which will store these data items in some way into what is known as a hash table. Now, it is very easy to understand that the first data item gets mapped to a certain address in hash table depending on the hash function. So we don't expect all these 4 data items to be stored in a sequential way because the storage depends on the hashing function. One more important term is in order. It's called load factor. So load factor of a hash table is the ratio of number of keys in the table to the size of hash table. For example, in this case, there are 4 inputs or 4 keys, and we have considered the size of hash table as consisting of 10 rows. So in this case, the value of load factor is 4 by 10 or 0.4. So it is very easy to understand that the minimum value of load factor is 0 and maximum value is 1. So load factor ranges between 0 and 1. 0 load factor implies that we do not have any data items to hash. Load factor of 1 implies that we have n number of data items, exactly n number of addresses in the hash table, so that depending on the hash function, each of these data items gets mapped accordingly. Well, it is very easy to understand that the load factor of, let us say, 1.1 is meaningless. For example, we cannot actually hash in 11 data items into a hash table whose size is just 10. It does not make any sense. Let us move on and discuss about different hashing methods available. Theoretically speaking, there are infinite amount of number of methods in the literature, but let us consider only 5 of them for our discussion. The first method is called subtraction method. In subtraction method, h of k, or the hash address that we want to generate using hash function, is defined as k minus n. Now please note, k is the value of incoming key or input, n is a constant. So if we consider a sample example here consisting of this data stream and assume that the value of n is 10, a simple table indicates the values of keys and h of k, that is the addresses generated. So first input data is 12, so 12 minus 10 is going to be 2. Second data is 23, so 23 minus 10 is 13. The list just goes on. So this table means that the value of 12 or key 12 will be stored at hash address of 2. Value 23 will be stored at an address 13. Value 34 will be stored at an address 24, so on and so forth. So how does this look pictorially? Pictorially, if this is the hash table and if the first column indicates the hash addresses, as I told you earlier, the content 12 will be mapped into hash address of 2. So at address 2, the data 12 exists. And then number 23 will be hashed into location 13. So location 13 exists here, and here we will have the data 23 being stored. The same thing is true for the rest of numbers. It is very easy to see here that remaining addresses have some junk numbers and we do not bother about them. This is because if I have to, let us assume that we have to search for number 60, since I know the method of hashing, which is subtraction method in this case, and since I also know the value of constant n, so 60 minus 10 will be done, resulting in a hash address of 50. So we directly go to that location and find the data, and hence constant search time is always guaranteed. The second method is division method. It is defined as h of k is equal to k mod n, where n is a constant and k is the input or the value of key. Please note, n need not be an even value. It can be any number, but the research has shown that n is usually selected to be a prime number. Consider the same example once again. Let the value of n be equal to 10. This even number is selected intentionally to show you an important aspect of division method. So the first incoming data is 12. So we perform 12 mod 10, resulting in answer 2. 23 mod 10 gets me 3. 34 mod 10 gets me 4. It is very easy to understand that data 12 is now being stored at location 2. Data 23 is now stored at location 3, and so on and so forth. Once again, how does this appear pictorially? This is how the division method is going to generate the hash addresses. Let us see it once again. Data 12 is stored in location 2. This is what we have. Data 23 is stored in location 3. This is being shown here. And the new incoming data 34 is stored at location 4. Now the data 45 is stored at location 5 as shown here. Data 60 is stored at location 0 because 0 is the hash address of this data. Data 78 is stored at hash address 8. The new incoming data 33 has hash address of 3. Well, what is the problem? The problem is location 3 already has a data stored as 23 sometime back. So we say that there is a collision. Collision because multiple keys are getting mapped to the same hash address. Similarly, when the incoming data is 90, 90 mod 10 gets me an answer of 0. I go to 0th location and I find that once again there is a collision because earlier data 60 is placed into location 0. So once again we have a collision. So this example shows that we have multiple collisions occurring. Well, what do we say? Are collisions good? Definitely not. Because if there are collisions, then what we have to do with the new set of data that have the same h of k or the same hashing address? So ideally, we want to have 0 number of collisions. Let us consider one more method, digit extraction method. In this case, we extract a prefixed set of digits. For example, if the input is k equal to 1234, we take middle two values and they are used for generating hash address. In this case, the middle two values correspond to 2 and 3, and hence 23 is the value of h of k for this particular input. Well, do I guarantee that we don't have any collisions? It is simply not possible. There can be some collisions depending on the data stream. Now, what is the basis for selecting just 2 digits in the middle? It is very heartening to see that we can define our own set of digits to be chosen for the purpose of framing the hash addresses. It is quite possible for us to select extreme left and extreme right digit to frame the hash address. If we do so, the hash address of this number will not be 23 anymore, but it will be 14. Once we decide on the digits to be extracted, we have to be consistent. The next method is called folding method. In this method, what we do is we partition the identifier or input into several parts and add the parts together to obtain the hash address. For example, if the input number is as shown here, we can always partition the input into a sequence of 3 digits as shown here, like 123, 203, so on and so forth. And then we add them up to generate a hash address of 699. Once again, one can have different perspectives on selecting different digits for the purpose of folding this huge number. The next method is called mid-square method. What we do is, in this case, we take a number, the number is basically a key or input, we square it and consider the middle value over here. Now in this case, the hash address is going to be 2. It is also possible to take middle few digits and square them to generate hash address. Consider this example. If the key is 121, we consider the mid digit, which is 2, we square it, and hence we frame the address 4. So this is how we generate h of k. Well, there are some issues in hashing. As we have discussed earlier, collisions are a big threat. Ideally, we would like to have 0 collisions, but that is simply a dream. There are many algorithms devised, many methods exist, which can have the number of collisions as less as possible, but 0 collisions are simply not possible. Then what is the answer? What do? We go for rehashing. There are basically 3 methods of rehashing we are going to discuss in the form of linear probing, quadratic probing, and double hashing. There is one more important issue with respect to hashing, and that's called clustering, and clustering is not good. The meaning of clustering is as follows. If you look at the right hand side diagram from the same previous example, this is the way in which the data are hashed into different addresses. Well, this part shows a heavy accumulation of incoming data, whereas the locations over here are empty. The locations over here are once again empty. So clustering is going to decrease the efficiency of hashing method. This is what we're going to see in the next few slides. Let us look at different types of rehashing techniques. The first one is called linear probing. On the left hand side, we have a hash table where using some hashing function, the addresses are generated and the data is stored. In this case, we have considered division method. Let's assume new data as 22, 46 and 92. So if the new data is 22, let us go with the same value of n as 10. So 22 mod 10 we perform to get an answer of 2. We try to go in here and place the data, but please note that there is a collision. Why? Because earlier 12 is stored into the same location. So what we do is we try to go to the next immediate location and try to search if it is free or not. If it is free, we place the data. Otherwise, this continues until I get the first free slot, and hence we place the data. The value of h dash of k indicates modified hashing function, and it is defined as h of k plus I mod n. It is quite easy to understand that if the next successive set of location is also taken by some other data, we keep on exploring the locations, and that is going to lead to performance issues. The second method of rehashing is called quadratic probing, where h dash of k is defined as h of k itself, but a term I square is added. Please note I varies with every iteration. On the left hand side, we have the same hash table displayed here, and the new incoming data is 22. The value of n is 10. So 22 mod 10 is 2. So if we go to this location, there is a clash or there is a collision. So we look at the value of I as 1. So 1 square is going to be 1. So earlier generated address plus 1 is done, and we go to that location, check if it is free or not, and then we store it. Let me consider 47. So 47 mod 10 is going to be 7. So we go to location 7 and we find that there is a free slot. We simply save it. What about 92? 92 mod 10 gets me 2. We go to this location. It is already taken. There is a collision. So what we do is we try to increment the value of I from 1 to 2. So 2 square is going to be 4. So whatever h of k we have generated, that is in this case 2 plus I square, that is 4 is done, and hence we go to location 6 and store the data. Well, it's a different story altogether if this location is also taken by some other data. The value of I keeps on varying continuously. What if the next data is 122? Once again, it is very easy to see that 122 mod 10 is going to be 2. We have a collision. We cannot go to next location. The value of I is 3 now. So 3 square is 9. So 9 plus 2 is done. So we go to location 11 and here we store the value of new incoming data. So this is how quadratic probing works. Next type of rehashing is called double hashing. In this case, we consider h of k, the earlier hashing function, and then we try to go for a different hash function altogether and generate a new set of addresses. As told before, it is not guaranteed to have collisions equal to 0, but collisions can be as less as possible. Let us consider one more important aspect of hashing. It's called collision resolution. In fact, in the literature, many solutions exist. One solution we are going to discuss is called separate chaining method. This is a very nice example where we have an array used to implement the hash table. In this case, the size of array is 5. Let's assume that the incoming data hashes into 0th entry over here. So instead of storing the data, what we do is we store a pointer and we make use of the dynamic memory management technique. So we perform malloc or calloc operation here. We create a node, place the data. So data is stored as a part of node which is pointed to by this pointer. Let's assume that the new incoming data also hashes into the same address. So what we do is we try to follow the pointer, we traverse through this linked list, we create a new node, place the data here and make it point to null. It is very easy to see in this diagram that if the new incoming data does not hash into, let us assume, location 1, then there is no any list at all here. This diagram also shows that location number 2 has total of 3 numbers hashed like this. So depending on the hashing address, we try to create a separate chain of numbers. So this is an example where we have statically framed a hash table and we keep on dynamically framing the set of data which hash into some address. So it is a very unique way of resolving any conflicts in terms of resolutions. This method is called separate chaining method. In the literature, many other collision resolution methods are also available. To summarize, we have gone through the basics of hash tables, hashing functions, collisions and clustering, and collision resolution. Hope this video was of some use to you. If it has done some good for you, please try to comment in the comment box and subscribe to the channel. Thank you very much.